Hi everyone, today we're back for a new video on oxygen not included, and today we'll see how to use petroleum's heat in order to produce power. The idea is that you're going to boil crude oil in order to get petroleum, so you would need to heat up the crude oil. So a way you could do this is with magma, just like I did here, but you could use other ways as well. So now if I were to use that petroleum, let's say for example in an oil refinery, but it could be something else as well, is going to delete that excess of heat because I'm going to have petroleum that is over 400 degrees because it requires 400 degrees in order to boil crude oil. So now if I consume that petroleum in this oil refinery, for example, it's just going to delete that excess of temperature, that excess of heat that I've created. So it would be nice if I could use that heat in order to produce power with a steam turbine. So that's what we're going to do now. So here we have a pump, a liquid pump that is going to pump that petroleum and is going to send it over to that room here. So how this liquid pump works, this liquid pumps needs to have an overheat temperature that is very high, so we need to use quite advanced material for that, unfortunately, because here we have a temperature of 425 degrees, and if you just use steel, for example, it's going to break that liquid pump. And also we use anhydrous sensors in order to make sure that there is enough petroleum in the room. The problem is that if there is not enough petroleum in the room and you keep putting crude oil in the room, it could just turn into sour gas directly, so that would be an issue. So now let's take a look at that room, and we can see that there is a thermo aqua tuner, and it's used in order to keep that steam turbine cool enough so it doesn't break and it keeps functioning. So if we quickly take a look at the piping system here, we can see that we use radiant pipes in order to keep our steam turbine cool enough so it doesn't break, it keeps functioning. And we can also see that we use a sensor in order to keep the coolant hot enough so it doesn't break the pipes. We also use temp shift plates, and that's because we want to get the temperature that is in the liquid here, petroleum, transferred to the steam that we're going to use. So there will be a better heat transfer thanks to these temp shift plates. And lastly, we need the steam in order to make that steam turbine function. And as I already mentioned before, the temperature is going to be transferred between that petroleum to that steam, and this is how we're going to cool down the petroleum and use the heat from the petroleum in order to feed our steam turbine and produce power. We also have a thermosensor here that is linked to our steam turbine, and this thermosensor is set to a temperature of above 200 degrees, because if it is less than 200 degrees, the steam turbine is not going to be at its full potential and is not going to produce the maximum power that it can produce. That's considering that the steam turbine has all its 5 inlets available and that it is able to take in 2 kilograms of steam. Otherwise, if it was not able to take in 2 kilograms of steam, maybe because there was one inlet closed or for some reasons that there wasn't enough steam, for example, then it wouldn't be able to produce its maximum power with 200 degrees. So ideally you want the steam to be at a temperature around 200 degrees, because if it's lower than 200 degrees, the steam turbine will not be able to produce as much power as it can. But if it's over 200 degrees, any degree over 200 degrees is going to be wasted because it's not going to produce more power for the extra degrees. One of the main disadvantages that I can see with this design is that the liquid pump here will require very advanced material. It will require niobium, or it can be another one, but it needs to support enough heat. It needs an overheat temperature that is high enough, so that is the main inconvenience. Which brings us to the next design, where one more time we will boil crude oil in order to get petroleum, so our petroleum will be hot and we can use that heat in order to produce power. But this time we are not going to use liquid pumps in order to bring the petroleum from one room to another. Instead, we are going to use mechanized airlock, and we are going to use an intermediate room. We have 2 sensors that are going to control that lock, so 2 hydro sensors. So here we will make sure that we have enough petroleum in the first room, and the reason is that if we have too little petroleum and we start pouring crude oil in that room, it could turn straight away into sour gas. So we want to keep enough petroleum in order to not run into that problem. And the second hydro sensor is used in order to make sure that there is space in the second room in order to pour some petroleum from the first room into the second one, otherwise there is no point to open that airlock. Then one more time we have 2 sensors in order to open that mechanized airlock with again an AND gate. So the condition needs to be met for these 2 sensors, like for the previous example it was an AND gate as well. The first sensor is a nitrous sensor and is going to ensure that there isn't too much liquid in the steam room, the final room, where we're going to be able to produce power. And the reason is that if we have liquid here up to the mechanized airlock, it will transfer heat with the petroleum that is in this room here, the intermediate room, and it's going to transfer heat as well with the first room. So that would be an issue because we would struggle to cool down the petroleum in the steam room, in the last room that we can see here. The second sensor is a thermal sensor, and it is set to below 205 degrees, and it is set to that temperature because we want to ensure that we don't waste too much energy, so we produce as much power as we can with that heat from the petroleum. And also it is to ensure that we have a temperature that is low enough so our liquid pump that is made of steel doesn't break. That was one of the issues of the previous design, so here we can use a material that is more affordable with that technique. Let's now see that in action. So the first door should open here because we have enough pressure in that first room from the petroleum, and that second door should stay closed because the temperature of the steam is still too hot, so you should see a transfer from some of the petroleum from the first room into the second room. So let's see that, and we can see that it fills the second room, and as soon as the second room is fully filled with the petroleum, it closes that door thanks to that sensor. So now the steam in that room is approaching 205 degrees, so that thermosensor should send a green signal and it should open that door. So we should also see that the steam temperature is going to rise when we open the door. So let's see that now. So the door has opened and we can see that the petroleum is moving in that room, and we can also see that the steam temperature is rising fairly quickly, and that's why the door is immediately closing. We can also see that the door is opening in order to fill the intermediate room as well. And that's pretty much it. We could also use an Atmos sensors connected to the liquid pump in order to make sure that we have enough petroleum in that room, because the less petroleum we have, the more sensitive it is to change the temperature of the steam, and therefore we are more sensitive to lose power because we're just going to delete degrees that we don't need to suppress. And another risk is that at the beginning when you set it up, if you don't have enough crude oils or petroleum here, the temperature change will be too high and the crude oil will turn into sour gas instantly, and that can cause issues because you will have to deal with that sour gas. But other than that, that's pretty much it.